take a look at this molecule. What happens if we swap the atoms over at each end one by one? Clearly, if we swap over this hydrogen and this hydrogen, you won't see any difference whatsoever. What happens if we swap this hydrogen with this methyl group? I'll draw the molecule out again just to be clear. I hope you can see that the two molecules are identical. It's just the question of flipping one of them over around the axes of these two carbon atoms, and the one molecule will become the other. But let's have a look at two different molecules and see if the same thing applies. What happens in this case if we swap this group with this group? I'll draw the molecule out again just so that we can see the difference. So here we have the CH3 and the H are the same as they were here, and the CH3 and the H have been changed over. Now the question is, are these two molecules the same? The answer is in fact no, they are not the same. The only way that we can convert this molecule here into this molecule here is by rotating the molecule around this bond. And in order to rotate the molecule around this bond, we actually have to break it. If we look at how the bond forms in the first place, this might be a little bit more obvious, because between the carbon and the carbon there's an overlap of two orbitals forming the new bond up and below the plane. So in order to twist around this central bond here, the orbitals would no longer overlap and you would break the bond. Therefore, we are doing chemistry. If you have to break a bond to convert one molecule into another, then the two molecules must be different. The molecules have the same formulae, but the atoms are connected together in slightly different ways. Therefore, they are isomers. But in this case, a pure description of which atom is bonded to which other atom would lead to similar descriptions for the two molecules, because it's the orientation of the atoms in space which is important. This type of isomerism is called geometric isomerism. Geometric isomerism can occur when there is restricted rotation about a particular bond in a molecule. In this particular case, the carbon-carbon double bond. However, not all alkenes can exhibit geometric isomerism. What we need for geometric isomerism is for one carbon at this end to have two different groups. Here we have CH3 and here we have H. And the carbon atom of the same double bond must also have two different groups. So that's a double bonded, two carbon atoms double bonded together, each of the carbon atoms having two distinct separate groups bonded to them. If we have this scenario, then we can have geometric isomerism. All that remains is for us to be able to label the two different molecules so that when I talk about a particular molecule, you know whether we're talking about this molecule or this molecule. And there are two different ways of doing this. We either use the cis-trans naming system, in which case this molecule would be cis and this molecule would be trans, because the big groups are on the same side, cis, or on opposite sides of the double bond, or we use the EZ nomenclature, which allows us to assign a label to compounds where there are more than one big group on each carbon atom. More about that later.